Let's review everything. Well, hopefully everything you need to know to do the Unit 7 exam. I'm going to go through it concept by concept. So let's go over the first major concept that will be tested anyway, and that is Coulombs Law. And this is the basis of all electrostatics. And that's what we're studying, electrostatics. It means there's no motion of charge. All the charges are fixed in place. There was a current to get all those charges to that location, but we're looking at it after those charges have settled down and stopped moving. So we have two fundamental particles, protons and electrons, that carry charge. Now, the ancients didn't know what these charges were. We do now. We know they were electrons and protons, but yet they developed a lot of this stuff without knowing that. Because we know we have two kinds of charge. One we call positive, and we know that positive charges repel, and unlike charges attract. There's a negative charge. These will attract each other. And, of course, negative will repel negative. And experimentally, they've determined that we'll call this side Q1 and this side Q2. And here we have a distance between them. We'll call that R. That the magnitude of these forces of repulsion or attraction is equal to, well, it's proportional to the charges, inversely proportional to the square of the distance between them. And that's it. That's all you can vary. You can vary the amount of charge, and you can vary how far apart that charge is. Now, a big quantity of charge we define to be the coulomb. The coulomb is a quantity of charge. Just think of it as a big basket of protons or a big basket of electrons. It's a heck of a lot, of that. We know that the fundamental charge, the charge on an electron, is equal to 1.6 times 10 to the negative 19 coulombs. Now, it is negatively charged, and a proton has this amount of charge, but of course it's positive. And if you want to know how many electrons are in a coulomb, just take the reciprocal of that, and you'll get a big number. Too big to really comprehend. And that's okay. That big basket of charge is called a coulomb of charge. So here, if we look at the units here, we have coulomb squared over meter squared. That does not equal a Newton. And we need some constant of nature that tells us how strong the electric force is in our universe. And we have that constant. It's K. K equals 8.99 times 10 to the 9 Newton meter squared per coulomb squared. Looks very similar, doesn't it, to the gravitational constant, except this is a billion, and the billion, newtons of meter squared per coulomb squared, and of course G is very tiny. It's 10 to the negative 11. Okay, very small. So gravity is weak unless you have a lot of mass. This is incredibly strong. The electric force is incredibly strong. But we have two kinds, so that if you have an electrically neutral object, you won't have any electric force. So that's a good thing, because we'd all blow to pieces if we were all nothing but positive charge. All right, so now this is in the r hat direction, because if you have like charges, negative times negative is a positive. So it'll be a positive r hat means away from the center. And of course, if you have a positive and negative charge, you multiply those together. That negative gets assigned to this r hat. It means it's attractive. Negative r hat means an attractive force. Okay? And I should put a vector hat here. And of course, this gives us the force of attraction between positive or between two different charges. But if I wanted multiple charges, I can do that. I can put, Q1, Q2, and Q3, I can have multiple charges. And if I want to know what is the electric force on Q1, I would just add them together. Well, this one's trying to bring me, in that direction. It's trying to attract. This one would be like this. And literally what you have to do is figure out what these vectors are. I would do it in I, j hat, notation. And then add them together as vectors. And that will give you the net force, the net electric force anyway, on Q1 due to Q2 and Q3. Okay, so this would give you the magnitude. And then you look, are these positive or negative, and then you assign the direction to that r hat. Okay. And so I could give you a problem, and one of the problems on the test will involve 3 point charges. And I want to know what is the force on one of the charges. Okay. And I try to do it so that it's not too computationally crazy, but make things a little bit easier. Okay, so that's Coulombs Law. And we have using Coulombs Law, we developed the electric field. So let's talk about electric fields. Okay, what is the definition of an electric field? Well, if I've separated charge somehow, let's say I put some positive charge over here and some negative charge over here. What I do is I look at the space in between that separated charge, and I put what's called a test charge in between them, and I notice, hey, all these positive charges are trying to push this guy this way and this way and this way and this way, and all these negative guys are trying to attract it this way and this way, So you got a whole lot of force. So I add up all of these electrical forces, and I say, what is the net electrical force on this guy? And I've got it. There's the net electrical force I get by adding all these guys up. And then I say, well, I'm going to say, well, this guy right here that I'm using to look at this region of space, this thing has some charge. So if I divide the electrical force on this object due to these other charges, if I divide it by this charge right here, this gives me, by definition, the electric field. The electric field tells me how intense an electric charge is going to get pushed. And look at the units. The units here are newtons per coulomb. And so if I put something there, that's how many newtons of force I get per coulomb of charge that I put there. And make sure that you understand that this Q naught is what I'm putting in the electric field. It's not what's causing the electric field. Students get confused sometimes about what charge they should use to figure out the electric field. It's the charge of the thing at that location in space where you're trying to measure the field, or calculate what the field is based on force measurements and knowing what this charge is. So I could take a little 1 coulomb. That would be awful, actually. 1 coulomb is a lot of charge. But I could measure the force on it throughout here, and I would get an idea of the electric field. So, but anyway, this is the basic equation for electric field. Of course, if the force is a point charge, if the charge causing the electric field is a point charge, let's say I squish all of these together, and I make like a point in space that's got all this positive charge, and I took all this negative charge and infinitely spread it out everywhere. Way out there in the universe, I could say, well, here's my test charge. I'll put my little positive test charge right here, and let's see, it's going to get forced away. Okay, and what is that force? Well, what's the E field here? The E field is the force, which is K from Coulombs Law. K, we'll call this big Q, times Q naught. This will be Q naught over R squared. R is the distance between the center of this and the center of this in the r hat direction. Well, the electric field this is the force. We divide that by the test charge. So the test charge cancels out. So what does this Q stand for right here? This is the charge of the that's at the center, at the point that's causing the field. Okay? So we just say that the electric field for a point charge is equal to K, Q, and you can call it little q or whatever. It's the Q, it's this Q over here, over R squared in the R hat direction. This does indeed have units of newtons per coulomb, because I took out one of the, K, Q, Q1, Q2. Well, I took out one of the Q's, so that gives you newtons per coulomb. So that's electric fields for a point charge. Of course, what we also did was if we take a whole bunch of point charges, let's say I have like a whole bunch of them. Here's a point charge, point charge, point charge, point charge, and I want to know what is the E field right here. Here's my test charge, Q naught. I would say, well, I'm just going to add all these together. So I would sum them. The electric field, E, would be equal to the sum of these. K, Qi over Ri squared. You would sum them all up. So here's Ri, there's this charge, we would sum all of these up. And of course I have to this is a terrible problem because I have to add a whole bunch of vectors together. And vector addition is kind of sucky. I mean, it's really tedious, but you have to do it. So this will tell you what the overall electric field is at that location in space. Well, what if I had a continuous charge distribution? What if this wasn't little discrete charges, but this was some weird surface like this, and I had a continuous charge distribution? Oh, lordy, lordy, I have to integrate now. I would pick one of these to be a little tiny charge, dq. And this summation sign turns into an integral sign. And it's going to be k dq over r squared in the r hat direction, although this becomes really problematic. R hat is going to change for each little dq you have. So this is really hard to do for a weird shape like this. In fact, if you have a weird shape like this, you would have to use numerical integration, where you have to use a computer to literally break this apart into thousands of little charges, and you would basically do this zillions of times. But of course, we don't have computers in here, so we don't do that. So therefore, the only way to do this is to have a problem where you can use this. Highly symmetric charge distributions, where you're basically not going to have to integrate, or if you do integrate, it's going to be a little bit easier. Then you will need to let's talk about electric field lines. So let's say I have electric field lines. Let's say I have a charged sphere or something with spherical charge symmetry. It doesn't have to be anything you want. Here's my test charge, and I go, ooh, it's being pushed like that. Well, now I put it on here. Let's put it right. Oh, it's not being pushed as hard, but still being pushed. Put the little positive charge here. It's getting pushed a little shorter. Well, we just connect all of these and make what's called a field line. This goes out to infinity. Well, what if I started here? Here's my little test charge. Oh, it'll push it like this, and like this, and like this, and like this, and like this. Okay? So the field lines tell you what direction the test charge is going to get pushed. And of course, look, what do I do in between here? Well, I could have drawn the field line there. If I put my little test charge here, it's going to get pushed like this. So the field lines tell you what's happening in space, what direction a test charge is going to get pushed. The number of field lines we choose based on how much charge is in there, and just, enough to fill the space around it so we have a good idea. I mean, you wouldn't, if you had a spherical charge or a point charge and you just drew one field line, that would be pretty boring. Of course, if I drew 37 field lines, that would be really unnecessary. Okay, yeah, you'd be, but you know, you draw enough. Now we did have some field line rules. And I am going to give you a little problem on the test where I give you some charges, basically point charges, and you have to draw an adequate representation of the electric field around those point charges that should obey the following rules. First of all, they start at positive. I should use a circle here because people are going to think that's a negative. Start at positive charge. And what else? End at negative charge. That's where they terminate. Now, how am I going to tell where it starts and where it terminates? You put an arrow on it. Every year, somebody on this problem, they draw a bunch of lines, but I can't tell what is, because they don't put an arrow on it. So I have no idea what direction the electric field is in for those field lines. So they lose some credit. Also, the number of fields lines is proportional to the amount of charge. So if I gave you a problem where, I've got some positive charge, maybe I've got 4 microcoulombs here, and I've got negative 2 microcoulombs here. Well, you got to draw the field around these two guys. Well, I mean, just follow the rules and say, okay, if I'm a positive test charge, I'm going to go straight over like this, and then I'm going to come around, like this, and maybe come around like this. These guys, this is going to be stronger. But here's the deal. I mean, I've got 3 lines of flux coming in here. What do I have to have over here? 3. I have to have twice as many field lines like that. So you have to have, if I only have negative 2 here, I can use 3 lines, but I better have 6, did I do that right? Yeah, I mean, I have 3 lines here. I need to have 6 lines over here. It needs to be proportional. So the number of field lines, don't worry about matching this number and this number. I got to have negative. I have to have 2 lines coming in here, and I have to have 4 in here. No, don't worry about that. Just have it proportional, and I got to adequately, represent the space around it. So shows the space around it. This one is the most subjective, shows the space around charges. And it's the most subjective, and it's the one I'm the most lenient on. I have had people do that. They'll give me, I'll give you let's say I had a point charge like this and a negative charge over here, and somebody just went, I mean, I literally have had people do this, and I go, nah, that just annoys me, -1. I mean, I left off the biggest one, right? There's going to be a new Ghostbuster movie coming out soon, I hear. Yeah. But anyway, don't cross the field lines. Okay, I did over here, but this isn't true. I mean, I was trying to do a separate problem. Don't cross the field lines, people, or 3 points will just immediately explode at the speed of light from your test. There will be a problem where you have to obey these laws. So if you want, maybe later on, you can create some problems for yourselves and check them out, and I'll come look at them. Okay. What if we have a uniform electric field? These are the easiest problems, really. If I have, let's say I have a negative plate over here, I've got some kind of a plate, positive charge over here. Let's say I've got a uniform field from positive to negative. Look at that. I'm obeying those field line rules. But this is a uniform field. E equals a constant uniform. Uniform means the field lines aren't spreading out. Well, that means that the force on my charge, let's say I inject a charge at a certain velocity like this. What's the force on that? Well, the force on the electric force is equal to the charge times the electric field. But if the field is constant and the charge is going to be constant, that means the force is constant. If that force is the net force acting on the object, then you've got constant acceleration. If you have constant acceleration, you can use kinematic equations. And in here, you've got projectile motion. So all that stuff that we studied with projectile motion will work. Yes?
When you drew it as an arc. Would it be as an arc?
Oh, no. You know what I did wrong here? The force is in this direction, isn't it? I kind of blew it. So I'll fix my drawing, not by changing this, but by changing this. Oh, now this is negative. So now the force is down, isn't it? So now it's like a gravity problem or whatever. Old-fashioned televisions used to do this back in the old days. They used to shoot a stream of electrons onto a phosphorus screen, and these little, they would light up, and they invented television that way. And those were not the good old days. The flat screens are way better. Way better. So, yeah, there aren't, anytime anybody reminisces about the old days, they're probably lying or just really forgetful because, or they feel guilty about something. All right, anyway, there are uniform electric fields. This is, and this is be equal to MA quite often. Or if you have an object like this, let's say it's got a negative charge on it, so the electric force is down, but maybe it's got gravity on it too, so you've got gravity pulling it down. So you could have two forces, and you have to figure out what the net force is, and so on. So don't be afraid to draw a little free body diagram of your charged object. Now, by the way, if I give you a proton or an electron or something like that, or an ion that's injected in, don't worry about gravity. If you're an atom, you don't even feel gravity compared to all these electric forces. Electric forces just are so dominant that gravity is negligible. Okay? But if I give you like a 10-gram object with a charge on it, now you got to worry about gravity. Okay, so that's uniform electric fields. Yay. And field lines, uniform, distributed charge, study that. Okay, now we get to chapter 24. Let's talk about electric flux. Couple ways of looking at electric flux. Really, it's the number of field lines I draw, sort of. It's really the number of field lines really depends on how much charge has been separated. Let me just, let's say I've got a positive charge here and a negative charge here on a plate. And let's say it's a uniform field. So I've got some plate right here, and I've got some metal plate over here, and I put some positive charge on it, and I'll draw one line of flux. Now let's say I'm going to put twice as much charge on it. So now I'll put a charge over here. Another line of flux, more charge, another line of flux. Another line, another charge, another line of flux. So I think you can see the way I'm doing this. These are called electric lines of flux. And the way I define how much flux there is really around the electric field. The more crowded these lines of flux are, the stronger the electric field. Now, how do I quantify the number of field lines? I mean, it's stupid to just count, oh, there's 1, 2, 3, 4, 5, 6, 7 lines of flux. There's 7 fluxes. Careful how you say that. All right, no. So we do have a definite way of measuring electric field. And so what we do is we say, hey, the amount of flux, and this is the symbol for flux. This is also known as the fluxing symbol, or just the flux symbol. Or anyway, this represents flux, and because it's electric, we'll put a little e in there. We're going to get to magnetic flux later on. All right, yeah, you can't wait. All right, now this is how we define electric flux. Electric flux is basically the electric field dotted with the area that field is going through. Now, it's kind of a weird definition. It's almost backwards. You can think of the electric field as being how crowded these field lines are together, or how many field lines you have penetrating per square meter. How many field lines per square meter you have. But we kind of rotate that definition over to here. And it's a scalar product, because remember, when I take an area, let me just do this three-dimensional. If I have a little area in there, ooh, that looks nice. Okay, there's my little area, and it's got lines of flux through it, but the direction of the area vector is always normal to that surface. Normal to the surface of the area itself. That's the only way to do it. And so when you take this dot product, you say, oh, look, the electric field line and the area vector, they are parallel to each other. And so this is, remember, this is E times A times the cosine of the angle between these two vectors. Really understand that area vector. If I've got an area, like this piece of paper has an area, the vector that represents its direction is this pencil sticking straight up at you. Okay? If I rotate the paper, I've got to rotate the pencil with it. So the pencil's supposed to be normal to the paper. All right. And represent the direction of the area. It's just don't think of it as the direction of the area. Think about how the area is oriented in three-dimensional space. That pencil tells you. And you treat it like a vector. So this gives me a definition for flux, for electric flux. And we're going to see in a second, it really does depend on how much charge is in there. Of course, if I've got a very curvaceous area here, ooh, look at that, yeah. I'm messing up this drawing really bad. Okay, if you put a ribbon in there or something, oh, now you got to figure out the flux through it. Well, that means the amount of electric flux is going to be E dot dA, okay? And so you'll have to integrate over this surface, which is a pain in the butt. I didn't say that. Now we took this idea of electric flux and we applied it to a situation where we have a closed surface area. We took this area and we say, if it's closed, we're going to say that E dot D. By the way, if the area isn't closed, it doesn't have to be closed. This will work. But if this area is closed, what does that mean? It means you have a surface area that is completely enclosing a volume of space, like a closed box or a ball or anything. That it's a surface area, but it rotates through three-dimensional space and closes in on itself, enclosing a volume. Well, if this is a closed surface, we say, oh, that's a closed surface integral. That's such a special situation. They have a special integral sign for it. Now, if I take some charge, I'll take another charge. And I got field lines like this coming through. Maybe there's negative out here. If I put a closed three-dimensional box in here, okay, you can see that for every line of flux that goes in, there's a line of flux that comes out. Now here's how we do these areas. This is kind of a bad drawing. Let me draw a nicer drawing, but it's going to be this situation in cross section. So you only see these areas. If I have an area like this represents this space over here. That's represented by this cross section. Well, here's my area vector. But look over here. Let's say it's a cube, same magnitude of area, but opposite in direction. It always points out, the area vector always points out from the interior of the volume to outside the volume. It always points out. Never points in. Okay, so these are all my area vectors, and you think you can see that these don't have any flux going through them because they're the area vector is perpendicular to the electric field vector, and so you got a cosine of 90 degrees, that's 0. But you do have flux coming in here. But look at this. Look at this right here. The electric field is going to the right, but the area vector is to the left. What's the angle between those vectors? 180 degrees. That means the cosine is going to be -1. This is considered negative flux for that volume. And then on this side, the area, it's coming out there, the area vector and the electric field vector in the same direction, 0 degrees. So it's positive flux. And it's easy to see here, but it can be shown for any shape. I could put a blobby or amoeba in there. That if I do this for a closed surface, I'm going to get 0. Because there's just as much flux going in as there is coming out. So if there is no charge inside this enclosed surface, the net flux is 0. There might be lines of flux going out there in the space, but there's 0 net flux through that surface. It's really easy to visualize. It's hard to say mathematically. Well, it's not hard to say that mathematically, but I mean it's easy to see. I think it's easy to see in your imagination. Well, what if I put charge inside there? And now we get to the magic of Gauss's law. Oh, so now we'll just call it Gauss's law. And we started with a point charge. If I put a point charge in there, I've got lines of flux like this. Here's my electric field lines. Of course, it's in three-dimensional space, but whatever. I am going to say that the amount of flux is equal to E dot dA, and this area is going to be closed surface. Well, I'm just going to close it with a sphere. Why? Because I can close it with anything I want. A cube, an amoeba, an ovoid, I don't know, whatever shape you can think of. I can do that. But I'm going to pick a sphere, and I'm going to make it concentric. The center of that sphere is going to be where that charge is. And then something beautiful happens. I notice that, the electric field is everywhere the same at the surface of my sphere. So this is going to be the same. So it's constant, so it comes out. Also, the little area vectors and the electric field vectors are parallel. So it gets rid of the dot product, right? It's just, E times dA times cosine theta. Well, cosine theta is always 1 if the two vectors are parallel. So what I do is I get this wonderful thing, E times the closed surface of dA. But what is this? Well, this right here is the electric field of a point charge, KQ over R squared. And this is the surface area of a sphere, which is 4 pi R squared. 4 pi R squared. And we get something, notice something wonderful happens. This R squared cancels out. Does it make sense that the R squared cancels out? Heck yeah, it does. Here's what this says. By this R squared, if I surround this with a smaller sphere, isn't there just as much flux coming out of it? Or a bigger sphere? Just as much flux is coming out. Just as many lines are coming out of it. So R doesn't matter. And hey, mathematically, that's what happens. And this tells me, the amount of flux is equal to K, let's do it like this, 4 pi K times Q. And by the way, if you want to use this 4 pi K times Q, go for it. It's fine. But we do have this thing called the permittivity of free space, which is which we call epsilon naught, is defined to be 1 over 4 pi K. That's by definition. And so what we get is the amount of flux coming out of there is equal to Q over epsilon naught. Very clever trick. Now, what does this mean? This Q right here, that's the charge that's inside here. Now, if I put some additional charges out here, you might have more fields going on. But if I'm just isolating this, just looking at this situation, the electric field, or the amount of flux coming out of this surface here just depends on how much charge is enclosed. Yes?
What is epsilon naught equal to?
What's that?
What's epsilon naught equal to?
Epsilon naught is 8.85 times 10 to the negative 12 meters squared per Newton meter squared, I believe.
Wait, Coulombs squared.
Or Coulomb squared. What did I say? Oh, what am I? It's Newton meter squared per Coulomb squared. Is that right?
Yeah.
No? Okay, yeah. Actually, I tried in my little brain to reciprocate the units for K. That's all you have to do, is reciprocate the units for the electric constant. And those are the units for epsilon naught. All right. Now we use Gauss's law. We have the full Gauss's law equals now on the test, I give you a problem where I ask how much flux is coming out of this shape. Well, that means I'm asking for this. What do you think the easiest way to do that is? Figure this out. How much charge is inside and divided by epsilon naught, and that is the quantity of flux. You don't have to use this. When do I use this part of Gauss's law? Yeah. We use this to find this part right here. Almost always, you use it to find the electric field given a highly symmetrical charge distribution, and it becomes very easy to do. Much easier to figure out the electric field using Gauss's law than Coulombs law. Coulombs law is evil if you have a continuous charge distribution. Why? Because you have to worry about vectors and all this, adding vectors together, and it's insane. But Coulombs law, if you understand how to use it, it's pretty slick. So, to use Coulombs law, we have to have a charge distribution, and using Coulombs law, using Gauss's law. We use Gauss's law to figure out the electric field for charge distributions. You're going to have three kinds. You're going to have spherical. Okay, and so you might have, and here are the three kinds you need to know. A point charge, which we actually use to derive Gauss's law. Not very interesting. Probably won't give you that one. Or you could have a sphere with a uniform charge distribution all through it. Or, and this is interesting because if I use Gauss's law to figure out what the field is outside, it looks just like a point charge. But if I use Gauss's law to figure out what the field is on the inside, you get a different expression. And then, or you could have a conductor where all the charge is out on the surface. Remember, for conductors, you cannot have an electric field inside a conductor. It's because if you did, you don't have an electrostatic condition. If you put an electric field in a conductor, charges are going to flow. And now you don't have electrostatics. So if you have a conductor, all the charge has to be outside on the surface and stuck there. And the electric field comes off like this. Okay. Now, well, here you have the amount of flux equals the integral of E dot dA over Q enclosed over epsilon naught. Well, you're always going to surround your Gaussian surface, or the surface you use to measure the amount of the electric field or the amount of flux or whatever. This this area is always chosen so that this is a constant. So this is always going to be E times 4 pi r squared equals Q enclosed over epsilon naught. Now what's hard? Figuring out what the charge enclosed is. There will be a problem on the test where you will be inside one of these uniform spheres. And you're going to have to derive it. You can't just write down all the equations and give that to me. I want to know that you can use Gauss's law to figure out how much, what the what the electric field is, but you have to figure out how much charge is enclosed in there. The other density, or the other is cylindrical symmetries. Okay, that could be, the simplest one is just a line like this. It'll be uniform. I'm not going to give you any crazy charge density where it's not uniform. Or you could have a cylinder where the charge is evenly distributed throughout the volume of the cylinder. Or I could give you a conducting cylinder. And where is the charge on a conducting cylinder? On the outside. What's the electric field inside? 0. Hope you remember that. Save you a lot of computational work. Okay. So what's my Gaussian surface going to be? What am I going to surround this with? A cylinder. And this, yeah, there'll be one inside. Oh gosh, and there'll be one outside too, maybe. And here, well, you can put a Gaussian surface on the inside, but how much charge is going to be on it? If you put it's going to be 0 charge in because all that's charged on the outside. Well, you go E dot dA for this equals the charge enclosed over epsilon naught. It'll be E times A. If you choose your Gaussian surface correctly. And what is the area of a cylinder that matters? The area of a cylinder. You need to know that the area of a cylinder is 2 pi r times the length. Oh, I forgot. Oh, no, I didn't. There's the area of a sphere, pi r squared. Area of a cylinder, 2 pi r times L. Make sure you know that. And that's what you're going to need to do. You're going to need to use Gauss's law to find the electric field for a spherical or a cylindrical charge distribution. There was one other, and that was a flat sheet. You have a flat sheet with charge on it, an infinite flat sheet, but I don't have enough room for that, so I'm just going to cheat by drawing arrows. Now what do these do? Well, they send up field lines Some of them are up, some of them are down. Okay, like this. So what you want to do is choose a Gaussian surface that matches that, and we just pick some surface like this, like that, and you say, okay, well, here we've got a certain amount of charge. Okay. And, we have to figure out what is the area of this. It's just A, and A. Well, this is the area, not of the Gaussian surface, though. This is the area that has charge on it. What is the area of the Gaussian surface that has flux going through it? 2A's. Yeah. So this is just E times 2A equals Q enclosed over epsilon naught. So this gives me E equals Q enclosed over 2A epsilon naught. And then, but how much charge is enclosed in there? Well, one thing I've neglected, because this little review is running into a 45-minute lecture now, just about done, is charge densities. Okay? When you're dealing with this guy, you've got, I'll go back to it, rho is equal to the total amount of charge in there divided by the total volume. Don't worry, I will not give you rho as a function of R or something like on the take-home test. Okay? This is the total charge of the total volume. So if I have to figure out how much charge is enclosed in here, well, the charge enclosed is equal to rho times the volume, but here's where you got to be really careful. This is the volume of the whole thing. What is this the volume of? The volume that is enclosed by my Gaussian surface. And this is where students go wrong. They get their R's mixed up. Am I talking about the radius of the whole thing? We'll call that big R. Or am I talking about the R of my Gaussian surface? We'll call that little r. All right? This, are you going to use big R or little r for this one? You'll use big R for this one. You use little r for this one. Because here you're trying to find out how much charge is enclosed by the Gaussian surface. It's the density by the volume of your contained by the Gaussian surface. Yes? Okay. Same thing is true here. Here we usually use to figure out how much we have a length. So we'll say, well, the charge density, which we'll call lambda, is the total charge divided by the total length. We'll call it total length, capital L, or whatever. So if you want to know how much charge is enclosed, well, use that. And then over here, well, this is charge smeared over an area. So we call that charge density sigma, which is the charge, divided by the area. Well, if I take this and, look what I got. Charge over the area. And this area A here is the area that has charge on it that's contained in my Gaussian surface. So this turns into E equals Q. I'm sorry, not Q. It turns into sigma over 2 epsilon naught. Last thing, if this, what?
What does the cylinder one turn into?
What is the what?
The cylinder one for this. What do you replace the cylinder one?
Oh, lambda. It's a linear charge density. Charge per unit length. This is charge per unit volume. This is charge per unit area. Now, What if this is a conductor? What if this is a flat surface, but it's a conductor? So here's my a conductor. Well, it's got charge smeared over its surface. I'm looking at it in cross-section. Well, none of the field lines can go down. Like on this one, this was just a sheet of non-conducting material. I put a charge on it. All of it goes straight up. So only one of the areas, if I put a thing like this, only one of these areas has flux going through it. So instead of 2A, you just have E times A. And so you have E just over the surface of a conductor is equal to the charge density over epsilon naught. The direction of it is normal to the surface. Has to be normal to the surface. If it was at an angle, it would push charges to across the surface. You wouldn't have an electrostatic condition anymore. Oh, that was long. But, I mean, I hope it put it all together for you. Let's just do it real quick. Geez, I used a lot of sheets of paper for this. Again, you got Coulombs Law. Tells you the forces. Tells you the relationship between charge and force. From there, we defined electric fields. Make sure you know the relationship between force, charge, and electric field. For point charges and for continuous charge distributions. And or a series of point charges. Make sure you can draw electric field lines. And you know the rules for electric field lines. Make sure you understand that if the electric field lines are uniform, you're going to have a uniform force, and now you'll have a uniform acceleration, and you treat it like a projectile in a gravity field. Then we defined electric flux. Electric flux, just kind of a representation of how much charge that has been separated. The more charge has been separated, the more lines of flux you would draw, depending on the situation. This led us to Gauss's law. And there will be 2 problems on Gauss's law. That's 20 out of 60 points is Gauss's law. So make sure you know how to use it. Okay. That is all.